Welcome to the video lecture for section 7-2, estimated a population mean, and this is for STA 2023. So the main concept of this section is to present methods to use a sample mean X bar to make an inference about the value of the corresponding population mean mu. So the main three concepts we're going to talk about, similar to the previous one, is the point estimate, confidence interval, and sample size. Now, first thing we're going to do is we're going to construct the confidence interval for estimating a population mean when sigma is not known. Now, there are two different ways that we can do this. If we know what sigma is, which is the population standard deviation, then we can use the z. If we don't know what sigma is, then we have to use the t, which is the one that we're going to introduce in these next few slides. So, some notation: mu is the population mean, n of course is the sample size, x bar is the sample mean, E is the margin of error, and lowercase s is the sample standard deviation. So some requirements: the sample is a simple random sample, and then there are two conditions. Either one or both of these conditions are satisfied. The population is normally distributed. In other words, the population where the sample was taken from is a normally distributed distribution, or the sample size is greater than 30. Now, margin of error, again, we're talking when sigma is not known. So the margin of error in this case is E, capital E, is equal to T alpha divided by 2, where T is your critical value, times S, which is your sample standard deviation, divided by the square root of n. Now, when we're using the T distribution, we use degrees of freedom, and in this case is the sample size minus 1, or n minus 1. Confidence interval: the confidence interval is associated with a confidence level, such as 0.95 or 95%. And alpha is the complement of the confidence interval. In other words, alpha and your confidence interval should add up to 1 or 100%. For a 0.95 or 95% confidence level, we have an alpha of 0.05 or 5%. So the critical value. T alpha divided by 2 is a critical T value separating an area of alpha divided by 2 in the right tail of the student T distribution. Degrees of freedom is n minus 1, is the number of degrees of freedom used when finding the critical value. So, original data: when using an original set of data values, round the confidence interval limits to one decimal place more than is used in the original data set. When we're using summary statistics of n, x, or s, round the confidence interval limits to the same number of decimal places used for the sample mean. So some key points about the student T distribution: if the population has a normal distribution and the distribution of T is equal to x bar minus mu divided by s divided by the square root of n. If is a student T distribution for all sample size n. Now, a student T distribution is commonly referred as the T distribution. Degrees of freedom. The finding a critical value requires a value of the degrees of freedom. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. For methods of this section, the number of degrees of freedom is the sample size minus 1. So finding the critical value. Critical value, T, alpha divided by 2, can be found using technology or a table. Now, technology can be used with any number of degrees of freedom, but the table can be used for a select number of degrees of freedom only. So we're going to be using technology to find the critical value for a T. Now, the student T distribution is different for different sample sizes. And so that's why we use degrees of freedom. And so you have to be careful because the value is not the same. When we did proportion, the value for a 90, 95, 99 was consistent. For a T distribution, it changes and is contingent on your sample size. Now, the student T distribution has the same general symmetric bell shape as the standard normal distribution, but is a little bit more variable. Now, a student T distribution has a mean of 0, just as the standard normal distribution. The standard deviation for the student T distribution varies with the sample size, but it is greater than 1, unlike the standard normal distribution, which is 1. As the sample size gets larger, the student T distribution gets closer to the standard normal distribution. Once you get to a certain sample size, the values for the critical values are actually the same, or get really close. So, procedure for constructing a confidence interval for mu. Verify that two requirements are satisfied: the sample is a simple random sample, or their population is normally distributed, or the sample size greater than 30. With sigma unknown, use n minus 1 degrees of freedom. Use technology of the T distribution table to find the critical value, and then evaluate the margin of error using capital E. Using the value of the calculated margin of error and the sample size, substitute the values into the formats for the confidence interval. Now, with an original set of data values, round the confidence interval limits to 1 decimal place more than using the original set of data. When using the summary statistics of n x bar s, we round it to the same number of decimal places as the sample mean. So, here's the first example. Find a critical value of t alpha divided by 2. So here we have a critical value t alpha divided by 2 that corresponds to a 95% confidence level given that the sample size is 15. Because the sample size is 15, the number of degrees of freedom will be 14. Now, the 95% confidence level corresponds to an alpha of 0.05. So there's an area of 0.025 in each of the two tails of the t-distribution. And then you can see the critical value here in the image, it's 2.145. So using technology, we find the critical value. And I will show this in class, how to use technology to find this, and also how to use Excel. Now, some point estimates for margin of error E from a confidence interval. Point estimate of mu, x bar, upper confidence limit plus the lower confidence limit divided by 2. The margin of error is the upper confidence limit minus the lower confidence limit divided by 2. So this is really similar to the proportion that we did in the previous lecture. The next thing is we're going to determine the sample size and required to estimate the value of the population mean mu. So again, here's some notation. The new one that was not in the previous one is sigma, which is the population standard deviation. Everything else is the same. Now, the first thing is that the sample must be a random sample. Now, the required sample size is found by n is equal to the critical value times sigma divided by the margin of error squared. Now, if the computer sample size n is not a whole number, we're going to round n up to the next larger whole number. Now, dealing with unknown sigma when finding the sample size. We can use the rule of thumb, the range rule of thumb, to estimate the standard deviation as follows, that sigma is approximately the range divided by 4, where the range is determined from the sample data. We start the sample collection process without knowing sigma, and using the first several values, calculate the sample standard deviation s, and use it in place of sigma. The estimated value of sigma can be improved as more sample data are obtained and the sample size can be refined accordingly. Now we're going to estimate the value of sigma by using the results of some of the earlier studies. So assume that we want to estimate the mean IQ score for a population of statistics students. How many students must be randomly selected for IQ tests if we want a 95% confidence that the sample mean is within 3 IQ points of the population mean? So the margin of error is 3 IQ points. For a 95% confidence interval, we have that alpha is 0.05, so z is 1.96. And so here, because we want the sample mean to be within 3 IQ points of mu, the margin of error is 3. Also, we can assume that sigma is equal to 15, and then we get that we need a sample size of 97. So among 1,000 of statistics students, we need to obtain a simple random sample of at least 97 of the IQ scores. With a simple random sample of only 97 statistics students, we'll be 95% confident that the sample mean x bar is within 3 IQ points of the true population mean mu. Now, if we somehow do know the value of s, the confidence interval is constructed using the standard normal distribution instead of the student t-distribution, so the same procedure can be used for the margin of error. Now, here's another example. Using 15 birth rates of girls given below, for which n is equal to 15 and x bar is equal to 30.9, we're going to construct a 95% confidence interval estimate of the mean birth rate of all girls by assuming that sigma is known to be 2.9. So in this case, we know sigma. So first thing is the sample is a random sample because the sample size is n is 15. The requirement that the population is normally distributed with a sample size greater than 30 can be satisfied only if the sample data appear to be from a normally distributed population. So we need to investigate normality. We're going to talk about this in class a little bit more, but here's a quick way to gauge normality. So the sample data appear to be from a normally distributed population. So then what you do here then is you just simply find the z-score of the values and you graph the x values or the values themselves against the z-score. And if they follow a nice straight line, then you'd be okay. Now let me show you something, which is I did that here. And so here are the samples that they gave us. One of the first things you have to do is you have to line them up from smallest to largest, and then the z-scores. And you can see that all I did was I took the actual value, and then I found the average of the sample, and also the standard deviation of the sample. and then I went ahead and graphed them. And they do appear to be on a straight line. Let me go back to this thing. Now, with a 95% confidence level, we have alpha is equal to 0.5, and we get a critical value of 1.96, sigma is 2.9, sample size is 15, so we find the value margin of error, and here we get 1.46760. Now, with x bar is equal to 30.9 and the margin of error is 1.46760, we find a 95% confidence interval as follows. And you can see using the formula we get between 29.4 and 32.4. Now, remember, this example illustrates a situation in which the population standard deviation is known, which is rare. The more realistic situation with sigma is unknown is considered in part 1 of this section. So, choosing an appropriate distribution. What do you choose, a t or a z? So, conditions. Alpha not known and normally distributed population, or alpha not known and the sample size is greater than 30, uses student t distribution. Now, alpha is known, normally distributed population, or alpha known and the sample size greater than 30, and in reality, alpha is rarely known. We use the normal z distribution. Now, the next thing is, which we won't talk about in this class, but if population is not normally distributed and the sample size is less than or equal to 30, we use what they call the bootstrapping method, or non-parametric method. And that's the end of 7.2. Thank you.